It's really a great honor for me to be here today. I just really always don't appreciate how long I've collaborated with the Indian groups for so large a fraction of my career, both as mentors and collaborators. And when I came here today, it reminded me, your director, Rajesh, and I were graduate students together at Princeton, and a colleague of ours who's also a classmate, Juan Maldacena, he invited me to give a talk at TASI or something like that. He didn't really ask what I wanted to talk about, and I talked about how we were going to discover the Higgs boson. But I realized he invited me because I was an existence proof that somebody could go as a graduate student in the 90s to Princeton and not become a string theorist. So, they didn't care what I said. It was just not string theory. And I was invited to give this talk today by my Collider colleagues. And I thought last night, I said, wait a second, this is again an existence proof. They wanted me to talk, show that there's a Collider physicist who also can do work in quantum sensors for neutrino projects. So I'll try to satisfy that existence proof as well today. But first, what I'd like to talk about is collider detectors. Where I've spent 30 years or so working on them. And they're fabulous objects. If we look at what they were able to do the Higgs discovery, the fact that two completely different looking detectors sort of had simultaneously about the same sensitivity so early on is really just a tremendous expression of how we developed lines of understanding of different detector technologies, knowing the weaknesses, which were robust, which were not, and they came together so well. However, I should say that these detectors were designed in the 90s. Most of the parameters were fixed then. We built them sort of 10 years after that, and we did make some major changes right before construction. But for the most part, many of the parameters were fixed, and we have upgraded them quite successfully to introduce new capabilities, much of which was the readout electronics and the triggering capabilities. But as you know, in maybe 5 years from now, we'll have more substantial upgrades to accommodate the advances of the accelerator community in their ability to produce the high luminosity fluxes. So we have hermetic timing detectors that can determine the T0. We have more radiation hard detectors that can survive the flux, and some sort of major upgrades. I don't know if this has a pointer. Yeah, to the tracking systems, different from what were installed at the original construction. But with that said, I do think that when we look to the future, we really should reassess the optimal set of parameters for a given measurement we want to do. These detectors were, of course, designed to do the Higgs discovery. Here's the detector, which my colleagues here in India and I collaborated on before, that was designed in the 80s. And in fact, there was an upgrade. There were some upgrades. The silicon vertex detectors were introduced in the 90s at all the LEP experiments and SLD, and we can't live without them anymore, and they're much bigger than their original version. So there were lines of development that has really enabled us to do things over the years, and we have to sort of look and see what the future measurements should be and what our limitations are. One thing I want to say is that this is a schematic view of the slice of the CMS detector, just to give you a reminder of the sort of the vertex detectors, the tracking systems, precise measurement of electromagnetic particles, followed by the full containment of hadronic showers, embedding all of those in a high field magnet, and then catching the flux of particles coming out with an outer hadron collider, and then instrumenting a return flux for muon identification and tagging. These were all chosen by the experiments really to do well at the different decay modes of the Higgs boson. And so if I take an example of the gamma-gamma reconstruction, a similar optimization was done for the accordion liquid argon for ATLAS. And what was most important, it turns out, was the constant term for the calorimeter. And in the early days of the, sort of the discovery announcement, we had to, signal over background weight it. You could sort of see the signal here. You would subtract out the background, and it looked fairly convincing. And we had that also in the ZZ star final state. If you look at the more recent publications, what people have locked into, and so you don't even have to do a background subtraction to see the signal anymore, because the detectors are understood well enough that they know what information they really needed to separate signal and background. And it took some time. Of course, there's an order of magnitude more data and it's more selective. But that is how the field has evolved. The field has evolved in such a way that they want the detectors to give them information that they need. They develop sophisticated algorithms to use it. And then, that's where the bulk of the power of sort of modern collider physics is. Now, of course, it helped that these were decay modes that didn't have fundamental backgrounds. I think this was the Landau-Yang theorem, and sort of well-chosen final states to design the detector based on. If we look forward to what we need to do, there's all sorts of leading parameters that really impose, big challenges, even for the tracking detector. The older detector that I mentioned had a tracking volume of about 0.5 meter, which is about the size of a trash can. And I think that was kind of roughly what, its capabilities were somewhat limited by that small radius. And so by pushing out to about 1.2 meters, which was done by the LHC experiments, really a lot more power and understanding what particles were being produced and how to separate them were there. And you'll see that many of the future colliders really want to push this out to more like 1.8 meters because the power of the precision tracking has really pushed things quite a bit. And on the inside, I think the upgraded HL-LHC detectors are going to push down to like 3 centimeters from the beam axis, which is really quite amazing. The issues that we always knew would occur with these detectors, there's a material budget, which drives on, how many sort of material interactions are occurring here that, affect both the tracking and future measurements, but the sort of the fraction of the 3D pixelated volume versus either a strip or a drift chamber, that we always knew that radius would push out as we learned more and more how to push data out of these detectors. If you look at the solenoids now have really changed quite a bit. Really a large amount of engineering have gone into them. And so the CMS solenoid might be considered really a hulk compared to the ones that are being proposed for the future. We support the entire hadron calorimeter and electromagnetic calorimeters on that inner volume, and they're designs in which this is only maybe a fraction of a radiation length thick, and much thinner and lower material. And so whether we place entire calorimeters within these or we put them in the middle or in front, allows us to be more flexible with having this larger tracking radius. We've also seen, and I think this is a repeated theme that we saw at LEP, at the parasitic projects at the LHC, and towards the future, which is that the muon system, it does give an important term, in complementing the momentum measurement of the central tracker. But once that radius becomes so large, a lot of the precision comes with just matching an ID. A lot of physics has gone into sort of, using this as an extended decay volume. So this LLPs, as mentioned earlier, and so that, just sort of maybe embracing that function of that larger enclosing volume might make more sense for future detectors since it's become a larger part of the program. And in the calorimeter section, this is, I'll give a specific example of the calorimeters in that, it's a challenging issue because a lot of precision for charged hadrons comes from the measurement of the track. And here I've actually modified the standard figure that we show in which the hadrons only interact in the hadron calorimeter. Unfortunately, that's not the case. They start to interact already with the first significant amount of material. And so, so much power of, for instance, the CMS calorimeter was improved by removing this measurement and replacing it with the track. The calorimeter made by Atlas is a much more precise, hadron measurement system, and you don't have to play this sort of balancing act between tracker resolution and the hadron calorimeter. But ultimately, there are, on order 10% of the particles are neutral hadrons, and there's nothing else you can do. So you need to still have very good hadron resolution if you want to push sort of the resolution of the objects you're measuring, as far as you can. So, you face all of these different choices, and then, how do you decide that you made the right choice? We know that, even for the phase 2 upgrades, that the transition radiation tracker, this sort of xenon gas system, really wasn't as successful as originally thought, and is going to be replaced with a full silicon tracker. Many of the future studies, whether it was ILD or CLIC or the muon collider or FCCEE or CPC, which is this one here, they end up being variants of a very similar base design. I think much of that came from the complexity of incorporating the so-called particle flow algorithms into these detectors to get this sort of extra bump on the ultimate precision. So I'm going to, sort of look into that a little bit more. I think what tells us we've made the right choice is to pose, sort of an important physics measurement that we really want to be able to do the best we can possibly do and make it a convincing case, across not just our field, but any field, and to make a detector that does that well, like we did with the Higgs detector. And of course, it's capable of doing other measurements as well as new theories come in and new things. But we want to show that we can do at least one measurement quite well. So if I take an example of some of the recent published papers on measurements that we could do, one thing that I've learned to appreciate in studying areas that are sort of complementary to the high energy collider physics, cosmology and astrophysics. In particle physics, we're quite happy with this picture of having a potential with renormalizable terms in which we can say that a scalar field rolled down this potential and gave us the electroweak symmetry breaking. But in other fields, they'll look at this and they'll say, well, that's wonderful. You've started off the universe with a field that has a very high potential energy everywhere in space. Of course, that's going to affect the expansion of space-time. The fall off of that, should be, also described with physical observables that are measured in the early universe. And what's been sort of discovered is that the models of new inflation, which were developed with the Higgs field in mind, really don't match what we've measured or what's been measured in cosmic microwave background and these sort of things. And so while this picture looks very nice and clean within particle physics, we really should think about the impact of our measurements of fundamental scalar fields, which I think we found the first one, and now we have to really find what other ones might be associated with the Higgs and sort of be able to help relate this to the problem of extending how the early universe came. John talked quite a bit about this on the fact that when you introduce matter content of the standard model, that this basic shape in the end at high field values can either go unstable, it could be metastable, it could be stabilized by an additional symmetry. I found that these studies were particularly interesting. In fact, it was maybe not well known, but it was one of the most accurate predictions of the Higgs boson before we discovered it, which was to postulate that the self-coupling vanished at the gut scale and the derivative of the self-coupling vanished at the gut scale. And so this sort of picture of the self-interacting potential sort of flattening out at this high scale is also particularly interesting possible clue at the beginning of LEP, one of the most important measurements we did was to make enough sine squared theta W effective measurements and running of alpha S and the fine structure constant at the Z boson, which I think is probably around 1/128.8, and to see, sort of what physics is happening at smaller length scales. And there's a similar association with the Yukawa couplings and for the Higgs self-couplings. And if you look into the sort of the brain power or the intellectual resources that have gone into studying these issues of inflationary fields, it's just vast. It's the best and the brightest people in our field, and they really put a lot of time into this. It took me about 10 minutes to find an Indian group with an incredibly interesting paper. This was a group in Kolkata, where, of course, you have to, the Higgs field, as I mentioned, doesn't have the right shape, so you have to use the so-called non-minimal coupling to gravity. And, it's a very interesting, compelling case for adding scalars to the standard model to try to understand how inflationary models can give you the right number of epochs of expansion. And so, so one thing you could say in particle physics is maybe we should help, resolve the, potential, uncertainty we have in what the shape of the Higgs potential is. Now, we know that from our studies over the last 10 years, it's been very hard to develop a case where we can produce enough di-Higgs bosons with our current, accelerator program, projections to make a sort of a very high statistical significance measurement. Of course, you can produce two Higgs bosons which are incoherently produced. What you're really looking for is the sort of the interference piece that comes when they're going through a trilinear coupling. And it actually, in the case of the LHC, reduces the number of di-Higgs events that you see on the final state. So in programs like the Higgs factory, where they have operating points of center of mass energy of like 240, where the HC it's near its peak, and regions past the TT bar threshold, but also have sort of a more substantial WW fusion portion, you can get important contributions to those cross sections that come from the trilinear coupling of the Higgs, sort of probing, the sort of loop contributions to the direct Higgs production and also to its branching ratios. And you can get, sort of three reference points. One comes from the percentage change to the cross section at that center of mass energy. We studied these kinds of changes at LEP quite precisely. If you look at the difference between the Born cross section and the QED corrected line shape of the Z width, and you want to measure the number of neutrinos, you realize you have to understand this correction quite well. In this case, the correction for the Higgs loops is about 1.6%, let's say. And so the goal in this case would be able to measure that to on order 0.2%, so that you can have, with individual measurement and then also the combination of these measurements, sort of, very substantial, greater than 5, if not 10 sigma test of the Higgs self-coupling that drives the shape of this potential. And this is not so different to, so for instance, the early delta rho measurements that we made at LEP to verify that the Higgs it has a component which is complex doublet, which satisfies custodial symmetry. These kind of, correction terms are really, sort of an important next probe for the Higgs sector and Higgs beyond it. We, of course, tried to do these things at LEP. This is an opal analysis. And of course, we never got, the best way to look at inclusively all the ZH production is to take one Z and have it decay to leptons, and then look at the recoil mass distribution from that. And of course, we were limited at LEP to everything below 120. This is with finite resolution. This was looking for a scalar at about 70. And so, you see a lot of ZZ production, which is you've seen here. And so the idea is if you push, a version of this for the FCCEE or one of the other machines, what does the recoil mass distribution look like? And here it is shown here. This is with a parameterized detector. And you can see there's a fair amount of background here. And it's a little weird that there's background because you have one Z that's going to dimuons, and you're computing the recoil off of that. And somehow you're still not either identifying the dilepton correctly, maybe the dilepton is radiating and you haven't picked up the photon that you needed, or you're having problem with the Z to tau tau. But what's clear is that the measurement is not so clean with the detectors that are currently being used to do these studies. And this is a case of a full sim with maybe a not optimized detector, but it looks very similar. So if I look at trying to design a detector that basically tries to push down this background to reach this sort of goal of greater than 5 sigma identification of the trilinear coupling, there's sort of a number of issues that come up, some of which is the statistical power, whether you have 2 collisions points, whether you're able to use recoils off of non-leptonic systems, and then just sort of how you treat the particles that you do measure in the leptonic recoils. And so one goes to often this sort of list of potential calorimeters that you could use to help address this issue of separation. This is sort of related in some way to the W mass measurement, where a lot of the difficulty of that W mass measurement actually was in the calorimeter, which I think will be continued to study. And so in the selection of calorimeters, you can look at the electromagnetic term, the hadronic term, but then ultimately there's a, sort of the particle flow capabilities of those detectors, which is the ability to sort of to match together those tracks and those calorimeters together. And so, the particle flow isn't just a convenient way of beefing up the resolution of an individual single particle measurement. The fact that the particles are bent in the magnetic field is also a very important thing. If you want to compute the jet invariant mass, you need to know the momentum at the vertex. And so being able to have that reconstruction is sort of critical to having that resolution. I think what was also not appreciated is the fact that when the pi-0 photons decay promptly, a good fraction of them leave the jets. And so you try to make the jet based on the clusters, but you only have half of the hadron decay particles in the particles that you're using to make the jet. And that, of course, is going to fundamentally limit your ability to separate Z's and Higgs in the final state. So with a more precise electromagnetic calorimeter, you can actually do a pretty good job at first combining those diphotons into hadrons and making sure that you only run the jet algorithms on the hadronic final states. So, when you look in detail at how the detectors are designed, this is about 1 inch of what would be called the high granularity calorimeter, which is also known as sort of particle flow calorimetry to much of the technologies that have been studied for future detectors. And you see that even though you can have lots of longitudinal segmentation, the sampling fraction of silicon is just very low. And so the question is when you design the detectors, is it better to have sort of more precision in the other measurements that you do make versus having lots of hits? And in the early days, it was convenient to have lots of little tracks and to try to use that to estimate the energy. But if you look ultimately at where we're going in terms of measurements, there is some balancing act that has to be really readdressed to get this is 2 photons from a pi-0 that are close to each other in the calorimeter, to get detector designs that actually to make very good energy measurements, not just track particles. So this was a recent study in which the detectors were evolved in a different direction. Instead of we segmented the crystals, we gave them dual readout capability, which allows you to look at what fraction is electromagnetic versus sort of hadronic breakup. We put timing layers, we put projective dual readout fibers. And sure enough, we were able not only to have the best raw calorimeter resolution for jets going in, the dual readout further improved it, and the particle flow algorithms made it, as best as the best particle flow algorithms. And this was just a very simple algorithm. And not only that, the jets, really have Gaussian resolutions. So, and this was hard to do, mainly because the tools are not really readily available to go in and reconfigure an entire collider detector and study and sort of an advanced associative algorithm that gives you, momenta of jets, and to look and see whether that helps you to get the overall cross-section of HC. But that's really the direction of where collider physics has gone. The task of the detector physicist is well beyond just making sure we can make good signal to noise on a MIP going through the detector. It really has to go through the full way. And in the case of the dual readout, there's all sorts of material physics that comes in on how to optimally get the Cherenkov and the scintillation light out with a dynamic range of the silicon photomultipliers, from the same crystal volume. So, when we meet these challenges, we see that there actually are a significant amount of material engineering that can go into really pushing to that limit. If we look at the sort of scope of the colliders that Frank has, discussed, the detectors are pulled in different directions depending on what the collider needs. Radiation tolerance was, pulled very heavily for the HLLHC. We'll see a lot of timing and granularity being pulled from muon collider designs. And whereas the EIC detectors are really, sort of looking more towards having very low thresholds and material budgets on the inner detectors. All of those are things that, based on the experience we've had at the LHC, that we have to make sure that the detectors are really producing a maximum amount of information for those designs, because ultimately that's where the key results come out. So let me switch gears for a moment, continuing on the topic of calorimetry, high precision calorimetry. A lot of the detectors that I showed before were using either optical photons or ionization of atomic systems to measure some number of quanta to convert into an energy measurement of deposited energy. If you think of an electron going into sort of a small heat capacitance object that's coupled to a thermal bath, then the pulse that you get out just by looking at the temperature variation of that goes up sharply as the heat capacitance goes down, and the response time of the system so that you can make a new measurement is more rapid for small capacitance. And so if you think of a problem in which you're trying to measure electrons that aren't in the tens of GeV scale but are in the eV scale, then you can design detectors that have very small stopping power, about 30 nanometers of gold and about 10 nanometers of titanium. And you can develop what's called a transition edge sensor that can measure these energies quite precisely with reasonably fast recovery time, about 130 nanoseconds, and look at different pixel sizes. And at first you might say, well, it's crazy to look at a calorimeter that's so small. But through everything I've shown you in terms of the pixel detector grouping and the silicon pixels that are used to measure photons, the scale of 50 micron by 50 micron is big. And so if you can make one pixel work well, and you have a technology for being able to read them out in sort of a multiplex system, then you can design larger area calorimeters that are based on this high precision technology. So the quanta in this system, this is a proximity sense effects supercurrent, are Cooper pairs that are being broken up. So the smallest quantum isn't EV, it's micro EV. And so this is an example of this detectors which we built and we've tested, where we shoot infrared photons at them. So photons about 0.8 EV each. And normally in particle physics, when we see this plot, 0 photon is the pedestal, 1 photon, 2 photon, 3 photon, you say, oh, that's easy, I've seen that before. But usually that's an internal gain mechanism in which the detector response will only give you these outcomes. This is actually a continuous energy measurement. The actual quanta is micro EV. So if I had a photon with 3000 nanometer, I would see a nice peak sitting here. So I'm actually able to measure a single infrared photon to better than 10% energy resolution over a dynamic range of up to about 10 eV. And the fact that these have some width is coming from probably electronic noise. But this sort of new capability of having high precision electromagnetic calorimetry working at the optical photon measurements introduces an important new capability. And so if you revisit a problem such as the neutrinos that are produced from the Big Bang, the neutrinos, of course, produced at the MeV scale, but the universe has expanded by roughly a factor of 1 billion since that time. And so the energies of those neutrinos are, in fact, their momenta have gone down to about a millielectron or 0.1 millielectron volt. Their energy, which is p squared over 2m, if they're massive, is almost in the nano eV. So you really sense that you can be really sensitive to just the mass observable, and we know from neutrino oscillations and precision cosmology that if you were to capture a neutrino on a tritium target, that you would see a 2-to-2 process in which the electron coming out from that capture is more energetic, the endpoint of the beta spectrum, by about twice the mass of the neutrino. Well, we don't know exactly what the absolute neutrino masses are, but we know that they're in this range. And so in the fact that I could measure using the calorimeter in the previous slide to this energy measurement level means that I could potentially launch a experimental program where I'm trying to detect not only evidence for the finite neutrino mass, which comes at the endpoint of the electron, because the electron can't carry away all the Q value because some of it goes to the mass. That gives these little thresholds here. But if I could scale up this experiment to a large enough size, I could detect the flux of neutrinos coming from the Big Bang, which is really the largest, by far the largest flux, accounting for nearly half of the particles in the universe. And so the way I can construct it, I have one part which I won't describe, which is a precision electromagnetic spectrometer, which allows me to remove most of the kinetic energy of this electron through a precision voltage, and then a free piece, which is just putting that final kinetic energy electron into my TES calorimeter and measuring it. So, I mean, this is a spectacular new development. I think what I've found is that, when you revisit or you look into unexplored areas of research, you tend to get new challenges and sometimes unexpected outcomes. So one of our challenges was to put tritium on a substrate that we could use as a target material. We decided to use, for various reasons, graphene. And at that time, we started the project about 10 years ago. You could get maybe 10 or 15% of the carbon atoms hydrogenated with tritium. Since then, we figured it out, and we get more than 90%. So within the last year, we've developed the lowest mass, highest capacity hydrogen storage system, reusable hydrogen storage system that's been developed. So it has a great societal impact. It looks wonderful from the point of view of what we wanted to achieve for our experiment. But the more we dug into this, we realized that when the neutrino is captured on the tritium, you can imagine that the helium-3 that's produced from it, it could fall into the ground state of the system that's holding it, like on a Mossbauer type effect, in which case the outgoing electron has maximum momentum. Or it could go into some excited state of the system, or in the case where you just assume that suddenly these particles are non-interacting and you assume that the helium is going into a plane wave, then in fact it sort of ruins the endpoint resolution of the picture I showed you before. So what we found is that we've engaged condensed matter theorists who are willing to collaborate with us, because we sort of need a whole new level of quantum engineered materials to remove this sort of atomic smearing term that affects our ability to see a neutrino observable. And if it's a very rich area of study. You get to interact in different areas of physics. And it's not clear there's a really good solution to this, but that's what it's like. So the thing I like about the quantum sensor direction, and this could have, I use the example here of a TES that's designed for electron measurements. I could have talked about a transmon qubit that counts microwave photons. It's very similar, physics. The other one might be used for axion detection. This one's using for neutrino mass measurement. But what's interesting about these areas is that we learn more physics. We could potentially bring these kinds of detectors into our collider area or launch new experiments. But it's, I would say, less guaranteed that you have, the development lines are just starting. It's less guaranteed that you'll have, sort of a measurement like, so like we can in accelerator collider physics, show that we reach the sensitivity. That doesn't mean it's not worth it. I think that what it means is that it's good to have, so of a direction in which you can continue in an experiment that is sort of more guaranteed to have certain outcomes, plus, this rich development line of quantum sensors that will sort of, maybe your students, or maybe if you're lucky, you'll have a time scale to actually launch a large scale experiment to be able to do this kind of work. So there's many innovations that I see coming in collider physics, putting precision timing throughout, trigger level tracking, trying to get more of the data out of the tracking system so that you can decide on keeping events early on. This development I mentioned of the solenoids, the evolution of the muon systems to sort of extended long-lived particle decay volumes. Most of the real improvements of the LHC detectors have been coming from the upgrades on the front end where accessible and digital processing. There's new systems where we have configurable trigger slices. You can actually go and try to learn what the backgrounds are for the model with the data that's coming through that you couldn't otherwise compute or record. You could have a theory that you're trying to test and you put in a trigger for it. You could run it for some period of integrated luminosity and then hand it over to the next group who wants to do a similar thing. So this concept of having a kind of user facility built into the collider detectors, I think, is becoming a real thing. There are people who want in the Higgs factories to do triggerless, open readout. And, I think overall, I wanted to emphasize that I think the role of computational and algorithmic development with the direct detector design has really become, pivotal. I think if we don't move in that direction, a lot of the collider physicists that we train will just go out in a data science area in industry. So I'm looking forward to these sort of changes. And since Sunanda is talking after me, I thought I would flash a detector that he and I worked on. And I think if I remember correctly, the Indian groups are responsible. These were uranium, depleted uranium sampling plates with gas proportional counters that were used for our hadron calorimeter. In fact, the uranium would just light the whole thing up like a candle, and then you had to figure out which were the matched hits, and then you get this nice picture here. But this almost looks like an old Atari game when you look at it. But these were good detectors, and I think a lot of what we're able to do with the LHC today is because we've been able to have such a great starting point and continued it on. Thank you.
Thank you, Chris, for this projection into the future. And okay, we have some questions lined up. Gagan.
Yeah, so thank you for the last slide. I mean, that reminded the PhD days. So on a serious note, on slide 17, if you can go back. Right. So is it fair to say, like, if you look at the next generation Hadron Collider experiment, one is on the calorimetry side, whether we talk of high granularity or dual readout, whatever you just said. But from the tracking side, I mean, given the experience from CMS and Atlas, I mean, one is talking of fully silicon-based tracking, right? I mean, that is the thing, because I guess the gas-based, given the experience of Atlas with I'm forgetting the name.
The straw tubes and the TRT.
Exactly. So is it fair to say like it's more like the CMS way of the tracking on the silicon side, or you think there is a?
Well, I mean, it's certainly the case, and you know, for the upgraded CMS detector that we went further, and we now have doublets to do, you know, sort of geometry-based momentum selection, and then tilted the layers so that there's less material effect. I think currently for the LHC, the full silicon trackers seem to be the right choice. You know, we're not pushing the physics as much on the constant term, you know, which is affected by the material thickness and how much goes up. Nice thing about the silicon is that, you know, since the days of you know, now they're quite willing to go to, you know, 100 micron thickness wafers and this sort of thing. So they can sort of tune the amount of radiation hardness they need and still have good signal to noise, which comes a lot from this front-end ASIC. Were you referring to the FCC
Yes, that's that.
Okay. Yeah, so those are really, I didn't really mention anything about those detector designs. They are really, that's a tremendous amount of stopping power that's needed by them. And, you know, there are still, you know, people who consider when you have a gaseous drift volume or an ionization cryogenic liquid, it is very common to at least put silicon on the inside and the outside because of the sort of the DCA correlation term. It's just hard to beat the resolution you get if you know where the track started and where it ended. And then you use a lot of the other parts just to do pattern recognition. I wouldn't eliminate the ionization systems as a choice. I think that many people were going to eliminate liquid argon from LHC until Roddick came and figured out how to do the right pull shaping to make that possible. And I think the liquid argon's done spectacularly. So it's more challenging, but there is definitely, I know from the circular colliders running on the Z peak, where they really want to collect Z's at 30 kilohertz, it is difficult to get the gas to neutralize in time.
So with vast experience on these detectors for different colliders, for the future generation accelerators and colliders, where is the maximum efforts needs to be put on, whether on the material or miniaturization of the detectors, or maybe the immediate would be with the timing and resolution on the computational part?
That's a very good question. I think that the first and foremost principle is don't believe somebody when they say that this has already been determined, this is the best detector. I mean, you have to look at what measurement you're trying to make and what parameters that are reasonable to vary. So for the crystal segmentation, we went down to centimeter squared sizes. For the precision hermetic timing detector, we went to 3 millimeter by 3 millimeter and put SIPMs on each side, which is 300,000 crystals. And they're made of LISO, which is an expensive material. But in the end, it turned out to be quite affordable. I think that and not only that, it was considered difficult to fit it in there. The difficulty with CMS, I actually had to redesign the carbon fiber structure to support the inner tracker and make room for the timing detector for the upgrade, because no one else wanted to do it. So I think that, what I'm particularly interested in, and I found this because I just launched a new long-lived particle trigger for run 3, is that I found that when the prompt part of the pulses appear in the different cells of the detector, in this case, I was looking at the calorimeter, they weren't aligned in time at all. They were off by, 20 nanoseconds, which you say, that's impossible. We should know everything by a nanosecond or better. Well, the deep part of the calorimeter with the new segmentation, it just wasn't aligned well. And so what I found is by introducing these new timing capabilities or having the small segmentation, you really prove to yourself as an experimentalist, the detector is doing what you think it's doing. Because people will go in and they'll believe the simulation more than the detector readout, and they'll say, well, there's just something wrong. We'll just correct the energy scale and we'll fix it up. And you realize that it's, not adding things lined up. So I think it helps us to make better use of our detectors to introduce more instrumentation at each cell level. So I think the timing and the energy and the segmentation, that's a sort of an unappreciated part of making sure your experiment works.
Yeah, thank you. It's a great talk. I don't have a question, but I just have a comment that you talked about quantum sensors, quantum calorimetry. Unfortunately, we had to cancel a talk on quantum bolometer. But astrophysics also has a lot of applications for these quantum-based sensors. Here in Bangalore, we have a lot of graphene-based expertise, and we are talking about quantum graphene-based substrate quantum bolometers that could detect 10 to the minus 19 to 10 to the minus 20 watts. So that should be useful for particle physics as well.
Yeah,
So
absolutely.
I'm glad you mentioned that.
Yeah.
Right.
Yeah, and in fact, I spent several years defining, trying to make a graphene field effect transistor in a pixelated format to be able to detect, single particle. The problem was that the conductance band was too sensitive with the geometry, so it would vary. And so people use this as a detector, to interact with the band and to get hopping, to get conduction. But, I found in order to get the planarity, I needed the boron nitride insulator, and those are very hard to get. So, a lot of the things that I think we could hope to do, like stiffening out the graphene to make it more uniform, are things that are only now becoming possible. So it really is a very exciting area, because I think people have ideas on detectors they want to do. And, if you ask somebody, how do you get the graphene, and you have to train them how to do CVD growth or taking them off, microcleaving them off another substance and this sort of thing. And, I think that, these graphene layers are amazing because really, except for hydrogen, no atoms can really flow through these diaphragms. So this issues of ion feedback in photodetectors, in the collection of electrons from cryogenic what do you call them? Drift chambers. A lot of that, backgrounds could be reduced if we introduce them just as passive layers. And they're very conducting, so they're also ground references.
Okay, with that, let's thank Chris once more. Thank you, Chris, for a very good talk.